I'm Chris Broadbent. I'm technical marketing for ST's Microcontrollers Group in the UK. First of all, before we go on, does everybody know who ST are? Have you heard of us before? 1, 2, 3, yeah. Alexander, we were talking on. You're familiar because you've been playing with our boards. Okay, so I'll do a couple of slides quickly just on who ST are, so to give you a bit of background, because it kind of sets the seed for the rest of the presentation. A lot of what I'm about to say, you've already heard from Alexander and Sadhanand already. So a bit of repetition, but I think that just reinforces how relevant what we're saying is and the work that Alexander's done in his coursework and how appropriate it is. So I'll skip that. So first of all, a bit about who ST are, in case you hadn't heard. We're not a small microelectronics company. We're not of the size of Intel or anybody like that. But we are a large company in the microelectronics world. Despite only a couple of people here, we do have over 45,000 employees worldwide, with about 7,500 working in R&D, so producing products. We design our own products. We use IP from vendors like ARM to produce our microcontrollers, but we design our own products. And we do that across 11 manufacturing sites around the world. So whether it's the front end and actually producing the silicon, or the back end where we package the devices up. We're very active in R&D. So we have about 9,500 patents, 500 produced pretty much every year. And where do you find ST's components? Everywhere. We're an electronics company, so you find, as you'd expect, we're in pretty much everything. Whether it's driving, homes, within industry, cities, across the globe. We're in pretty much everything where you need electronics. And we split that across all our various families, so whether that's the micros that I look after, or power electronics, sensors, etc. With a main focus across two big verticals, smart driving and Internet of Things. So these are the two categories that you hear most about in the news. Everybody talks about IoT and smart driving. And this is where we focus our product roadmaps into these areas. And they're key to ST's portfolio and our strategy going forward. So that's a bit about ST. Now on to what we are actually here to talk about. Embedded engineers, or engineering. So I think we've probably seen a couple of these points before. Today's engineers, when they go out into industry, what do they need? Well, increasingly, Alexander mentioned it, industry expects people to just be up and running from day one. An engineer turns up and they expect them to be able to get started, and just what the skills they already have are relevant to what they want to do. So they need to get those skills before they actually go out into industry, whether that's transferring from one job to another, or whether it's coming out of university freshly into a new job. But in terms of microcontrollers, engineers are facing increasingly complex products. Now, it's a long time since I was at university, but we did Z80s, 8051s, etc. Very basic, with only a few bytes of memory. Very basic microcontrollers. Now microcontrollers, they have the core in it, they have flash built in, they have interfaces like I2C, C, USB, all that kind of thing. Lots of complex devices. And it's very easy to get lost in all that and think it's very complicated, but when actually you need to learn about the fundamentals of microcontrollers. But embedded engineers come from multidisciplinary backgrounds, not necessarily electronics. It might be somewhere else. So they might need to know a bit about embedded engineering from a civil engineering point of view. from mathematics or just pure computer science. And then not everybody comes in needing all the skills. Obviously they're there to learn skills, but they might not have everything they need, so some basic fundamentals. So, and they work at different levels. So we need to be able to adapt what's being taught to suit those different levels. So how do we do that? So we need to give them, students, when they're within education, the experience and the tools they need to go out into industry. So they need to acquire it while they're here, and that's from the point of view of coursework that's relevant to what's in industry now, whether that be through projects or placements when they go out, whether it's like a sandwich course, something like that, where they're going out into industry, or more likely projects suitable for it. And they need to do it with something that's relevant to industry now and probably will be in the future. And also need to be looking at embedded systems for non-electronics engineers. So what level do you pitch the coursework at for that? Quite often students, if they're not electronics engineers, don't need to know the details of how the microcontroller works. They just need to know how to use it. So they're what they need to learn. How are they going to start learning it? So they're going to need tools to make that easier. So whether that's software tools or hardware tools, evaluation boards, like the boards Alexander's been using as part of his workshop, his courses, or the tools. So whether it's the ARM embed environment, etc., to give them the ease of use. And maybe, if we're looking at different levels of students or different capabilities or even different years throughout as students get more and more knowledge and more capable, maybe they need a choice of languages to develop in, or a choice of APIs to suit the particular project. And in terms of learning, hardware and software examples or information to find out how something works. So you're looking at reference examples to how to make the I2C work, or information on how to solve a particular problem. And increasingly, shared knowledge through forums and communities online. So there are many different products that can provide that solution. From an ST point of view, we'd like to think that the focus would be on the STM32, which is our flagship microcontroller. So ST was the pioneer of producing microcontrollers with Cortex-M core. Currently we're the market share leader of the Cortex-M cores, and we produce micros based on all of the Cortex-M cores that are available today. And we can also look at it from a point of this is more to do with industry, but it's kind of relevant here in that we produce our products for a minimum of 10 years. So a student learning on one of our micros now, at the end of their course, will still be going into this industry with a relevant background in a product. The products will still be there. And in terms of, again, more towards industry, but maybe looking at various courses, the portfolio, the key here is the portfolio of STM32 is very, very wide. So whether you need a micro that's excels in ultra-low power, excels in performance because you need to do some highly complex task, or even you just want something cheap, there's an STM32 around there that will suit that. Just to give you a flavour of that, I won't go into the details. We have a massive range of STM32s, so pretty much, as it says there, an STM32 for pretty much any project. So any project that your student wants to do, we could probably find an STM32, whether it's chip level or a board, to suit that. And as to give you an idea of the size of the base and how relevant the STM32 is to industry, we have more than 50,000 customers worldwide. We've sold 3 billion. I know Sadnan put up a slide about the number of ARM cores being shipped. We've sold 3 billion STM32s worldwide so far, and we sell 32 of them every second. So that's how relevant it is to industry. You've seen a picture of one of these before. So this is the kind of hardware that enables students to learn. We produce all of these for the different cores, Cortex-M cores, whether it's, and basically different boards with different amounts of GPIOs. That's how to look at it. Small 32-pin devices, 64-pin devices, 144-pin devices. They all have one common feature in that all you need is a USB cable and a laptop or a computer to use them with. You don't need anything else. You connect it up with the USB cable and then you can start work. Nothing else required. They're all Mbed enabled, so students can start up using Mbed and develop their code immediately. Plus, micro's one side of it, but you need it to do something. Now you can have an LED on there, and a button, you press the LED. These ones only have one button, I'm afraid. One button and one LED. But you might want to do some real world sensing, etc. So from ST's portfolio, we can take different boards, different add-on boards, expansion boards and shields, and produce a prototype that maybe has some motor control, some sensing, some connection, so whether it's Bluetooth or some other form of RF, to connect together to produce something real world that the student might want to do. And we call that our open development environment. I mentioned about different APIs and different levels to suit. To start with, you may use low-level APIs, or you might use Mbed as a starting point, giving you portability across all devices. But there are also some cases where you need to use the micro, but you don't need to necessarily know the details, so you might want to go further on, whether it's Java or MATLAB, etc. You have that flexibility across all the STMicros. I'll skip that slide. Software examples. I mentioned software examples as a form of students being able to learn. You know, it's very good to look at examples and see. So there are, as with anything to do with ST and with the Cortex, there are a number of ways of doing that. I've just picked out two to start with. We can provide examples of how to use our hardware and IP for everything, for all devices, whether that's the I2C or the memory interface, etc. We can do that. And obviously, ARM Mbed has their examples built in as well. So we've got the blinky LED in there to start from. Students need to gather information from other places, not necessarily just for examples. So whether that's all the information associated with our products is available on our website, as you'd expect. Information about the boards and how they fit into Mbed is obviously online as well. And then there's communities. Information is shared around. People, ask questions online these days and get their answers. They don't come necessarily to the vendor of the hardware first. They'll go somewhere else and ask across forums how to find out information, how to make things work. We're kind of trying to back that up and trying to, in a way, pull people back towards the vendor, us in this case, by supporting them with a community where people can go and find solutions and ask questions how they work. So that's the STM32 and ST, how it fits into education. As an example, you've already heard one example of a curriculum based on the STM32. We also have, there was an example at UCLA where a course has been developed along the similar lines, a foundation course in engineering that uses the STM32 and a number of other ST products to give a basic understanding to all engineering students, not just electronics engineering students. So it's based on a device called the center tile, which, to give you an example of what that is, you saw a picture of this board earlier. This is the 64-pin STM32 board, and you might add on to it add-on boards with, this one's the Bluetooth connection, but you might have sensors, so you build up a stack of 3 or 4 boards to produce it. Quite a bulky item. So if you want to just mock up the hardware and write some software, then that's great, but if you actually want to, if you're an engineering student and you want to do some real-world data capture, it's a bit clunky to go strapping to somebody either onto their wrist or to something where you want to measure the data. So we've developed a new device called the sensor tile, which is what this curriculum is based on. It's this thing, which you probably can't see at the back. It's a postage stamp size. It has all of that functionality on this little board. So it's got the micro, it's got MEMS microphone, Bluetooth connectivity, and sensors, gyroscope, and accelerometers, etc. So all of that on there. So it makes it very useful for students to be able to go and do real-world data capture. So I've basically said what this slide says. You take all those boards and you shrink it down into that little tiny tile. And the reason for using that and for the curriculum being developed at UCLA was that UCLA was seeing struggling numbers of engineering students coming in. And they had a lack of coursework that was suitable across the engineering discipline. You know, they had coursework suitable just for electronics engineers, but that didn't really suit the entire engineering education population. And so they wanted to teach students across engineering about embedded systems and give them the tools necessary to go and acquire data within their own specific disciplines, whether that's attaching this to somebody's wrist and analysing basketball throws, etc. They were able to do that and acquire the information and go off. So it made it very easy for them to acquire that information and the data and then go and analyse it for what they wanted to do. So it was introduced last year, and it's been seen as a very successful curriculum across the board. Seen a number of cases of students being hired because they had relevant experience in a microcontroller. I won't read that out completely, but it was seen as very important for students to be able to show that they had relevant experience in the microcontroller world. And if you want to read up more on that, it is all online, so you can go to our website and it's based on there. If you just type in to our search box, sensor tile curriculum, you'll find that link.
That's
okay.
it. Thank you.
You're welcome.